Welcome to Spring LIB.
Okay, so we've got to predict the direction of the equilibrium for the following acid-base reactions. So to begin with, I will redraw this. And we're told the pKa of these various acids. Okay, so I want to point something out here, and that's that you can actually do this problem purely mathematically if you're given these pKa's, right? And the way that you would do that is you know that this is an equilibrium. And in fact, that equilibrium constant K is equal to 10, right, to the pKaH of the conjugate base. So this is the conjugate base minus the pKa of the acid. Okay, so what does that mean? Well, pKaH is saying, look at the base on the left-hand side of the equation. Okay, that's acetone. Well, the pKaH is the base, it's the pKa of the protonated form of acetone, i.e. this, right? This is the protonated form of the conjugated base. And so the pKaH is negative 7.3. Okay. Okay. Now, we are asked to subtract the pKa of the acid on the left-hand side of the equation. Remember, everything here is with reference to the left-hand side of the equation. So this is our conjugate base on the left-hand side. This is our acid on the left-hand side. So the pKaH is in reference to this being our conjugate base, and this is the protonated form of our conjugate base, and the pKa is in reference to the acid, which in this case is the hydronium ion. So we subtract negative 1.7 or add 1.7, and we get 10 to the negative 5.6. Okay, and so that tells us that K is going to be much less than 1, which means that the equilibrium will favor heavily the left-hand side. Remember, a positive, or a K that's, the greater the K is, the more the right-hand side is favored, and the smaller K is less than 1, the more the left-hand side is favored. So it looks like you've got the right answer, but mathematically that's how you do this, right? You compare the pKaH of the conjugate base and the pKa of the acid. The other thing to do is you could just say we're going to favor the form, if we compare the acid on the left and the protonated conjugate base on the right, the one who has the higher or the less negative pKa is going to be favored, right? It's like saying hydronium's not as acidic as protonated acetone. Therefore, it's more likely that the hydronium will dominate because it's not as acidic. So it makes sense that if we've got to pick between hydronium having a proton or protonated acetone having a proton, we should pick the one that's least acidic or least likely to give up its proton. Okay, now let's move on to the second part of the equation, question. So now we don't have, values given for pKa, but we do have some clues as to the relative pKa's. Okay. know yet which way this favors. Okay, first question is, what's the acid on the left? What is the acid on the left? This is our acid. Okay, where's our conjugate base? This is our conjugate base. How do we know it's our conjugate base? That's not protonated, and the version on the right is protonated. Okay, and over here, if we wanted to do the pKa thing, which we can't do, obviously, we'd say K equals, so let's call this pKa equals, we don't know. And what's our pKaH in reference to? Well, it's this acid right here, right? Right, that's the acid form of our conjugate base, pKaH. Okay, so we'd say pKaH minus pKa. Okay, and so the question is, right, if we're going to do pKaH minus pKa, which of these is going to have a higher pKa and which of them is going to have a lower pKa? We've got to compare the pKa of this, which we don't know, we haven't been given a value, to the pKa of this. Right? Well, what's the difference between them? The only difference is this chlorine. And what does that chlorine do? What is that chlorine doing there? And what effect will it have on the pKa? Well, remember that chlorine is electronegative, right? Chlorine is going to pull negative electronic charge to itself, right? That's basically what it's doing. What's the effect of that? Well, in this case, if we look at the conjugate base of that acid right here, it's the function of this chlorine is to distribute this negative charge over a wider part of this molecule. This chlorine stabilizes this negative charge. It makes this a stronger acid than it would be. So the chlorine is making this pKa higher than it would be if it weren't there. That means this pKa is bigger than what should be exactly the same but without the chlorine, right? pKa is bigger than pKaH. That's the takeaway. Or sorry, I should say the pKa is more negative. This pKa is more negative. pKa more negative than pKaH due to chlorine stabilizing this structure right there. Okay. So we've got this number is more negative than this number. That means that K is going to be, this is going to be some positive number. Right? That's basically what we get out of this. If we subtract a more negative number from a less negative number, we end up with a positive number. So we're going to get 10 to the something. So what's going to be favored is the right-hand side. Does that make sense without looking at math? Let's see. We want to favor the side, whichever is the weaker acid should be protonated. So is this the stronger? So we're comparing the strength of this acid to this acid. Well, we reasoned about why this acid is stronger, and it has to do with the chlorine. So this is the stronger acid, and this is the weaker acid. And we want to pick the side that the weaker acid has the proton. This is the side where the weaker acid has the proton. So it makes sense that we're favoring the right-hand side. Okay. That's a few different ways to look at that problem. Hopefully that made some sense.